At this very moment, you are traveling through time. Not in some poetic or metaphorical sense. Literally, physically, measurably, every atom in your body is hurtling forward through the dimension of time at an extraordinary rate. You cannot stop it. You cannot slow it down by wishing. You cannot speed it up by wanting tomorrow to arrive faster. But here is what will absolutely shatter your understanding of reality. You can change the rate. You can actually alter how fast you move through time. And the method is shockingly simple. You move through space. That is it. The faster you move through space, the slower you move through time. And the slower you move through time relative to everyone else, the more the universe ages without you. This is not science fiction. This is not a thought experiment that lives only on chalkboards. This is measured. This is confirmed. This is happening right now to satellites above your head, to astronauts on the International Space Station, to particles created in the upper atmosphere, and to protons smashing together in underground tunnels in Switzerland. Today we are going to go on a journey into one of the most profound, most unsettling, and most beautiful discoveries in the entire history of human knowledge. We are going to understand why the universe has this rule built into its very structure, why speed and time are connected, why traveling fast means watching the universe grow old without you, why a person on a spaceship could age 1 year while the Earth ages 70, and why this is not some strange exception to the rules of physics, but is in fact the deepest rule of physics itself. In this video, we will start with a real experiment. A real, physical, documented experiment that proved this effect using nothing more than atomic clocks and commercial airline tickets. We will then build from the ground up. What is time? What did Newton think? What did Einstein discover? How does a simple light beam bouncing between two mirrors prove that time must dilate? We will go through the mathematics in a way that anyone can understand. We will explore what happens to you physically as you approach the speed of light. What you see, what you feel, what happens to the stars around you. We will walk through scenarios. What if you traveled to Mars at half the speed of light? What if you traveled to the nearest star at 99% light speed? What if you traveled to the Andromeda Galaxy and came back? How old would the Earth be? We will explore the twin paradox, the most famous thought experiment in all of relativity, and resolve it completely. We will connect time dilation to gravity, to black holes, to quantum mechanics, and to the very nature of reality itself. And by the end, you will understand something that very few people on this planet truly grasp. You will understand that time is not what you think it is. It is not a river flowing at a constant rate. It is not a backdrop against which events happen. Time is flexible. Time is personal. Time depends on what you are doing, how fast you are moving, and where you are in the gravitational field of the universe. And the faster you travel through space, the more of the universe's time you sacrifice. The more birthdays pass without you. The more history happens without your participation. The more the cosmos ages while your clock barely ticks forward. Let me start by telling you something that might seem like a small fact, but is actually extraordinary. Right now, as you watch this, there are roughly 31 satellites orbiting the Earth as part of the Global Positioning System. These satellites tell your phone where you are. They help airplanes navigate. They guide ships across oceans. And every single one of these satellites has a clock correction programmed into it that accounts for time dilation. If engineers did not correct for the fact that time passes differently on those satellites than it does on the ground, your GPS location would drift by approximately 10 kilometers every single day. Within a week, GPS would be completely useless. Within a month, you could not find your own house. The correction that prevents this chaos is not based on some engineering approximation. It is based directly on Einstein's theory of relativity. Both special and general relativity contribute. The satellites move fast, which slows their clocks down by about 7 microseconds per day. But they are also higher in Earth's gravitational field, where time runs faster, which speeds their clocks up by about 45 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds per day relative to ground clocks. And so, 38 microseconds per day are subtracted from every GPE's satellite clock to keep them synchronized with Earth. This means that every time you open a map application on your phone, you are relying on the physical reality of time dilation. You are relying on the fact that time is not the same for everyone. You are using Einstein's discovery to find the nearest coffee shop. Now, if that small fact makes you pause, if it makes you think, wait, time actually passes at different rates depending on how fast something is moving or where it is in a gravity field, then hold that thought, because we are about to go much, much deeper. Let me take you to October 1971. The specific days were October 4th through 7th. Two scientists, Joseph Hafele, a physicist from Washington University in St. Louis, and Richard Keating, an astronomer at the United States Naval Observatory, were about to conduct one of the most elegant and important experiments in the history of physics. And they did it in one of the most surprisingly simple ways imaginable. They bought commercial airline tickets. Here is what they did. They took 4 cesium beam atomic clocks. These were the most accurate timekeeping devices available at the time, capable of measuring time to within billionths of a second. They placed these 4 clocks on regular commercial airliners, not military jets, not spacecraft, regular commercial flights that you or I could have booked a seat on. First, they flew eastward around the entire world. The flights had multiple stops because no commercial plane could circumnavigate the globe non-stop in 1971. They changed planes, carried their clocks with them, and kept meticulous records. Then they flew westward around the entire world. After each trip, they brought the airborne clocks back to the United States Naval Observatory and compared them with the reference clocks that had stayed on the ground the entire time. The predictions of relativity were specific. Flying eastward, the clocks should lose time because they were moving faster relative to the non-rotating frame. The Earth rotates from west to east, so flying east means you are adding your airplane speed to the Earth's rotation speed. Your total speed through space is higher, therefore your clock should tick slower. Therefore, when you return, your clock should be behind. Flying westward, the prediction was different. Flying west means you are partially cancelling out the Earth's rotation. Your total speed through space relative to the non-rotating frame is actually lower than the ground. So your clock should gain time relative to the ground clocks. The results came in, and they matched the predictions of relativity almost exactly. The eastward flying clocks lost 59 nanoseconds, plus or minus 10 nanoseconds. The theory predicted they should lose 40 nanoseconds from kinematic time dilation and gain an additional amount from gravitational time dilation for a net prediction of minus 59 nanoseconds. The agreement was remarkable. The westward flying clocks gained 273 nanoseconds, plus or minus 7 nanoseconds. The theoretical prediction was 275 nanoseconds. Again, extraordinary agreement. These results were published in the journal Science, Volume 177, Issue 4044, on July 14, 1972. 2 papers, back to back. One on the eastward experiment, one on the westward experiment. Think about what this means. In 1971, 2 scientists carried clocks on regular aeroplanes, flying at regular commercial speeds of roughly 500 to 600 miles per hour. And when they compared their clocks with identical clocks that had stayed on the ground, the clocks disagreed. Not because they were broken, not because of some mechanical error, but because time itself had passed at different rates for the traveling clocks and the stationary clocks. The clocks that moved through space at a higher speed experienced less time. They were literally younger than their stay-at-home counterparts. By only billionths of a second, yes, but the effect was real, measurable, and exactly what Einstein had predicted 66 years earlier in 1905. Now, here is the question that should be burning in your mind. If flying at 500 miles per hour for a few days causes a difference of billionths of a second, what happens if you travel at 500 million miles per hour? What happens if you travel at 90% of the speed of light? What happens if you travel at 99%? 99.99%? The answer is that the effect does not just scale up linearly, it explodes. The relationship between speed and time dilation follows a curve that gets steeper and steeper as you approach light speed. At the speeds of everyday life, the effect is negligibly small. But as you push toward the speed of light, it becomes overwhelming, dramatic, universe-altering. A person traveling at 99.99% of the speed of light experiences time passing at roughly 1/70th the rate of someone at rest. For every year that passes on their ship, 70 years pass on Earth. 70 years of history. 70 years of births and deaths. 70 years of progress and change. All happening while the traveler ages just 12 months. If you are watching this and your mind is starting to race with questions, good, that is exactly where you should be right now. If you are thinking this cannot possibly be true, this must be wrong, this violates common sense, that is exactly how the greatest physicists of the early 20th century felt when they first encountered these ideas. But unlike common sense, which evolved to help us survive on the African savanna, the mathematics of relativity has been confirmed by every single experiment ever designed to test it. Not some experiments, every single one, without exception, for over a century. So take a breath, hit that like button because this journey is going to be extraordinary. Subscribe if you want to explore more of the universe's deepest secrets, and let me know in the comments what you find most mind-bending about time dilation. Because we are just getting started, and the deeper we go, the stranger it gets. Now, to truly understand why speed affects time, we need to first understand what time actually is. And the truth is, this is one of the deepest questions in all of physics. For most of human history, the answer seemed obvious. Time is the thing that flows from past to future at a constant rate. It is the thing that clocks measure. It is the background rhythm of the universe, ticking away identically for everyone, everywhere, regardless of what they are doing. This was essentially Isaac Newton's view. In his masterwork, the Principia Mathematica, published in 1687, Newton wrote about what he called absolute true and mathematical time. He described it as flowing equally, without relation to anything external. In Newton's universe, time was like a perfectly steady drumbeat. Every observer, everywhere in the universe, would agree on what time it was, how much time had passed between two events, and which events were simultaneous. If a star exploded and a bell rang on Earth at the same time according to one observer, then they happened at the same time according to every observer. Period. No ambiguity. No disagreement possible. This made intuitive sense. It matched everyday experience perfectly. When you and a friend synchronize your watches and then separate for a day, you expect to find your watches still synchronized when you meet again. And in everyday life, at everyday speeds, this is exactly what happens. The differences predicted by relativity are so small at walking speed. at driving speed, even at aeroplane speed, that you would need atomic clocks to detect them. So Newton's picture of absolute time served humanity brilliantly for over 200 years. It allowed us to predict the motions of planets, the trajectories of cannonballs, the timing of eclipses. It worked. Until it did not. The crack in Newton's perfect picture appeared in the late 19th century, and it came from an unlikely source. It came from the study of light. In 1865, a Scottish physicist named James Clerk Maxwell published a set of equations that unified electricity and magnetism into a single framework. These equations, now called Maxwell's equations, are among the most beautiful and powerful in all of physics. And they contained a remarkable prediction. They predicted that electromagnetic waves exist and that they travel at a specific speed, approximately 300,000 kilometers per second. This was the speed of light. And here was the problem. Maxwell's equations gave the speed of light as a fixed constant, not relative to anything, not relative to the source, not relative to the observer, just a flat, absolute number. 300,000 kilometers per second. Full stop. This created a deep contradiction with Newton's physics. In Newton's world, all speeds are relative. If you are on a train moving at 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour, an observer on the ground sees the ball moving at 150 kilometers per hour. Speeds add. This is simple, obvious, and fundamental to Newtonian mechanics. But what about light? If you are on a spaceship moving at half the speed of light, and you turn on a flashlight pointing forward, does an observer on the ground see the light traveling at 1.5 times the speed of light? According to Newton, yes. According to Maxwell, no. The speed of light is always the same. Always, this was a contradiction. Newton and Maxwell could not both be right. Physicists of the late 19th century tried to resolve this by proposing that light travels through a medium, an invisible substance filling all of space, which they called the luminous ether. The idea was that light's speed was fixed relative to this ether, just as the speed of sound is fixed relative to the air. If you move relative to the ether, you should be able to detect this motion by measuring slight changes in the speed of light in different directions. In 1887, two American physicists, Albert Michelson and Edward Morley, designed an extraordinarily sensitive experiment to detect Earth's motion through this supposed ether. Earth orbits the Sun at about 30 kilometers per second, so as it moves in different directions at different times of year, the speed of light should vary slightly, depending on which direction you measure it. Their apparatus, called an interferometer, was sensitive enough to detect differences far smaller than what Earth's orbital speed should produce. The result was stunning. Nothing. No difference. No matter which direction they measured, no matter what time of year, the speed of light was identical in every direction. Earth's motion through space made no difference whatsoever. The ether did not exist. Or if it did, it was completely undetectable, which in physics amounts to the same thing. This was a crisis. The most fundamental principles of physics were contradicting each other. Something had to give. Either Newton's rules about how speeds add together were wrong, or Maxwell's equations were wrong. Given that Maxwell's equations had been confirmed by countless experiments and were responsible for practical technologies like radio, most physicists were very reluctant to throw them out. But modifying Newton seemed equally unthinkable. For 200 years, his laws had been the bedrock of all physics. Enter Albert Einstein. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper titled On the Electrodynamics of Moving Bodies. This paper is now recognized as one of the most important scientific documents in human history, and its genius lay not in complex mathematics, but in Einstein's willingness to accept what the experiments were telling him and follow the logic wherever it led, no matter how strange the conclusions. Einstein started with two postulates, two assumptions, both based on experimental evidence. First, the laws of physics are the same in all inertial reference frames. An inertial reference frame is simply one that is not accelerating, one moving at constant velocity. This postulate says that no experiment you can perform inside a sealed laboratory will tell you how fast that laboratory is moving in a straight line at constant speed. The laws of physics look the same whether you are stationary or moving at 1,000,000 miles per hour, as long as you are not accelerating. This was not particularly controversial. It was actually a principle that existed in Newtonian physics as well, called Galilean relativity. The second postulate was the revolutionary one. The speed of light in vacuum is the same for all observers, regardless of the motion of the light source or the observer. This is what the Michelson-Morley experiment demanded. The speed of light does not change based on how fast you are moving. If you fly toward a beam of light at half the speed of light, you still measure that beam approaching you at the speed of light. Not at 1.5 times the speed of light, just the speed of light. If you fly away from a beam of light at 90% the speed of light, you still measure that beam approaching you at the speed of light, not at 10%. The full speed of light. Always, every time. No exceptions. Now, when you accept both of these postulates simultaneously, something extraordinary happens. Something breaks in your everyday understanding of the universe. Because if the speed of light is the same for everyone, then something else must be different for everyone. And that something else turns out to be time and space themselves. Let me show you why with one of the most famous thought experiments in physics, the light clock. Imagine you build a clock that works like this. You have two mirrors, one at the top and one at the bottom, separated by exactly 1 meter. A single photon of light bounces between these mirrors, going up, hitting the top mirror, bouncing back down, hitting the bottom mirror, bouncing back up, over and over. Each time the photon completes one round trip, 2 meters of travel, the clock ticks once. Since light travels at a known constant speed, you know exactly how long each tick takes. It takes approximately 6.67 billionths of a second. This is your clock. It measures time using the most fundamental constant in the universe, the speed of light. Now, imagine this light clock is sitting on a spaceship, and the spaceship is stationary. You are outside the ship, watching. You see the photon going straight up and straight down, up and down. Simple. Each tick takes 6.67 nanoseconds. You and the person on the ship agree perfectly about how fast time is passing. Now the spaceship starts moving to the right at high speed. The person on the ship sees nothing different. They are at rest relative to their own clock. The photon still goes straight up and straight down from their perspective. Their clock still ticks at the same rate. Everything inside the ship is normal. But what do you see watching from outside? You see something different. The photon still has to travel from the bottom mirror to the top mirror. But while it is in flight, the ship has moved to the right. So from your perspective, the photon is not going straight up. It is going diagonally. On a diagonal path, from lower left to upper right to reach the top mirror. Then it bounces back down on a diagonal from upper right to lower left to reach the bottom mirror, which has also moved further to the right. The photon, from your perspective, is tracing a zigzag path. And here is the critical point. A diagonal path is longer than a straight vertical path. The photon has to cover more distance to complete one tick of the clock when the ship is moving than when it is stationary. But the speed of the photon has not changed. Einstein's second postulate demands it. Light always travels at the same speed. It cannot go faster to compensate for the longer path. So what happens if the photon has to cover a longer distance at the same speed? It takes more time to complete one tick. The moving clock ticks slower. From your perspective, watching from outside, the clock on the moving ship is running slow. Each tick takes longer. Time on that ship is passing more slowly than time for you. This is time dilation. And notice that there is nothing special about this light clock. It is not that this particular clock slows down because of some mechanical effect of motion. Every clock on that ship slows down. Mechanical clocks slow down. Biological clocks slow down. The heartbeats of the astronauts slow down. The chemical reactions in their body slow down. The electrical signals in their brain slow down. Their thoughts slow down. Their aging slows down. Everything. Because it is not the clocks that are affected. It is time itself. Time in that reference frame is genuinely passing more slowly, and the amount by which time slows down can be calculated precisely. The formula is elegant and simple. The time dilation factor, called gamma, equals 1 divided by the square root of 1 minus v squared over c squared. Here, v is the speed of the moving object, and c is the speed of light. Let us see what this gives us for different speeds. At 10% the speed of light, which is roughly 108 million kilometers per hour, gamma equals 1.005. Time slows down by 0.5%. Barely noticeable even with sensitive instruments. At 50% the speed of light, gamma equals 1.155. For every second that passes on the ship, 1.155 seconds pass for the stationary observer. A 15% difference. At 80% the speed of light, gamma equals 1.667. For every minute on the ship, 1 minute and 40 seconds pass outside. At 90% the speed of light, gamma equals 2.294. For every year on the ship, 2 years and 3 months pass on Earth. At 95%, gamma is 3.203. For every year on the ship, over 3 years pass on Earth. At 99%, gamma is 7.089. For every year you experience on the ship, 7 years pass on Earth. At 99.9%, gamma is 22.37. For every year of your life, 22 years pass on Earth. At 99.99%, gamma is 70.71. For every year of your life, over 70 years pass on Earth. At 99.9999%, gamma is 707. For every year of your life, 700 years pass on Earth. And as you get closer and closer to the speed of light, gamma grows without limit. It approaches infinity. At exactly the speed of light, gamma would be infinite, meaning time stops entirely. Look at that progression. At everyday speeds, the effect is negligible. But it does not stay negligible, it grows. And it grows in a way that accelerates viciously as you approach light speed. The difference between 99% and 99.9% is not a small step. It is the difference between 7 years per year and 22 years per year. The difference between 99.9% and 99.99% is the difference between 22 years per year and 70 years per year. Each additional 9 added to the speed dramatically multiplies the time dilation. This is why the speed of light is truly a wall. You cannot reach it, because the energy required grows in the same way. The closer you get, the more energy each additional increment of speed requires, growing without limit as you approach light speed. But here is something I want you to sit with. something that often gets lost in the mathematics. The person on the ship does not feel anything strange. Their heart beats normally. Their thoughts flow at a normal pace. They eat breakfast, and it takes a normal amount of time. They watch a movie, and it lasts the normal duration. Nothing inside their ship gives any indication that anything unusual is happening. They are not in slow motion. They are not frozen. From their own perspective, they are completely normal, and it is the rest of the universe that has sped up. If they could look out their window and watch Earth, they would see Earth spinning faster, see seasons changing faster, see years flipping by like pages in a book blown by wind. The universe outside their ship is fast-forwarding while they live at a normal pace. This raises a beautiful and important question. Let us say I am on a ship moving at 90% the speed of light relative to Earth. From Earth's perspective, my clocks are running slow. But from my perspective, I am stationary, and Earth is moving away from me at 90% the speed of light. So should I not see Earth's clocks running slow? And the answer is yes. In special relativity, the situation is symmetric as long as both observers are in inertial frames, meaning not accelerating. I see your clocks running slow. You see my clocks running slow. This is not a contradiction. It sounds like one, but it is not. It is simply a consequence of the relativity of simultaneity, which we will explore shortly. The apparent paradox only becomes a real problem if we try to bring the two observers back together and compare their clocks directly. That is the famous twin paradox, and we will resolve it completely later. For now, just understand that time dilation is real, it is symmetric in special relativity, and it becomes asymmetric only when one observer changes their state of motion, that is, when they accelerate. Now let me take you deeper. Let me explain not just that time dilates, but why it must dilate. What is the deep reason? What is the universe actually doing? There is a beautiful way to understand this that was introduced by the physicist Brian Greene, building on the mathematical framework laid down by Hermann Minkowski in 1908. And it starts with a remarkable statement. Everything in the universe is always traveling through spacetime at exactly one speed. The speed of light. Wait, that cannot be right. You are sitting still right now. You are not moving at the speed of light. Except you are. You are just not moving through space at the speed of light. You are moving through time at the speed of light. Here is the idea. In our universe, space and time are not separate entities. They are woven together into a single four-dimensional fabric called spacetime. And every object in the universe is always moving through this spacetime fabric at a fixed speed. The speed of light. This is a constant of the universe. You cannot change it. You cannot choose to go faster or slower through spacetime. You are always going at exactly c. But here is what you can do. You can change the direction of your motion through spacetime. Think of it with a simple analogy. Imagine you are driving north at exactly 100 kilometers per hour. All of your speed is directed northward. Now you turn slightly to the northeast. Your total speed is still 100 kilometers per hour. That is fixed. But now some of your speed is directed eastward and some is directed northward. Your northward speed has decreased because you diverted some of your total speed into the eastward direction. The more you turn toward east, the less of your speed goes toward north. If you turn completely east, all 100 kilometers per hour are going eastward and 0 are going northward. Now replace north with time and east with space. When you are stationary in space, all of your motion through spacetime is directed through time. You are plowing through time at the maximum possible rate. The speed of light. This is normal. This is what it means to be at rest in space. All your spacetime velocity is aimed through the time dimension. Now, you start moving through space. You walk, drive, fly. Some of your fixed spacetime speed gets diverted from the time direction into the space direction. Your total speed through spacetime has not changed. It is still the speed of light. But now, some of it is going through space, which means less of it is going through time. Your speed through time has decreased. Your clocks tick slower. Time passes more slowly for you. The faster you move through space, the more of your spacetime speed is diverted from time into space. At the speed of light through space, all of your spacetime motion is in the space direction. None is left for time. Your motion through time is zero. Time stops for you completely. This is why photons do not age. A photon travels at the speed of light through space, which means it has zero speed through time. From its own perspective, no time passes. Ever, a photon emitted from a distant galaxy 13 billion light-years away arrives at your eye having experienced exactly zero elapsed time. For that photon, its emission and its absorption happen simultaneously. The entire journey, from our perspective, spanning billions of years, is for the photon literally instantaneous. This picture also explains beautifully why the speed of light is the ultimate speed limit. You cannot exceed the speed of light through space because your total spacetime speed is fixed at the speed of light. You cannot go faster through spacetime than you are already going. The speed of light through space means you have diverted everything from time to space. There is nothing left to divert. You cannot steal more speed from the time dimension because there is already zero in the time dimension. You have maxed out. This is the wall. Not some arbitrary rule imposed from outside, but a geometric consequence of the structure of spacetime itself. This concept was formalized by Hermann Minkowski, who had actually been one of Einstein's mathematics professors. In 1908, 3 years after Einstein published Special Relativity, Minkowski gave a famous lecture in which he said, and I am paraphrasing, that henceforth, space by itself and time by itself are doomed to fade away into mere shadows. Only a kind of union of the two will preserve an independent reality. He was right. Space and time are not separate, they are spacetime. And the geometry of spacetime is what causes time dilation. Let me add another layer of understanding here. When we talk about objects moving through spacetime, we can draw their paths on what is called a spacetime diagram. This is a graph where one axis represents space and the other represents time. Your path through spacetime, the complete record of everywhere you have been and when you were there, is called your world line. If you sit still in space, your world line is a straight vertical line going upward on the diagram. You are moving only through time, not through space. If you move at constant speed, your world line is a straight line tilted from the vertical. The faster you move, the more your world line tilts toward the horizontal space axis. And here is the key geometric fact. In spacetime, the proper time you experience, that is, the time that actually passes on your own wristwatch, is related to the length of your world line. But spacetime geometry is not like ordinary Euclidean geometry. It is what we call Minkowski geometry. And in Minkowski geometry, a straight world line between two events has the longest proper time. Any other path between those same two events has shorter proper time. This is the opposite of what we are used to in ordinary space, where a straight line is the shortest path. In spacetime, a straight line is the longest time path. This means that if you stay in one place and do not accelerate, you experience the maximum amount of time between any two events. Any deviation from this, any speeding up, slowing down, traveling and coming back, results in you experiencing less time. This is the deep geometric reason why the faster you travel, the more the universe ages without you. By moving through space, you are taking a shorter path through space-time, which means less proper time passes for you compared to someone who stayed put. Let me now show you that this is not just theoretical beauty. It is hard, cold, experimental fact. And the evidence comes from multiple completely independent sources. First, muons. Muons are subatomic particles that are constantly being created in Earth's upper atmosphere. When cosmic rays from deep space, mostly high-energy protons, slam into molecules in the upper atmosphere about 10 to 15 kilometers above the ground, they create showers of particles. Among these particles are muons. Now, muons are unstable. They decay radioactively with a half-life of about 2.2 microseconds. This means that after 2.2 microseconds, half of any collection of muons will have decayed into other particles. 2.2 microseconds is an incredibly short time. In that time, even traveling at the speed of light, a muon could only cover about 660 meters. Most muons are created at altitudes of 15 kilometers or more. Even at the speed of light, they should decay long before reaching the ground. At their typical speeds of 99.94% of the speed of light, a simple Newtonian calculation says they should almost all decay within about 600 meters of their creation. But they do not. We detect enormous numbers of muons at ground level, not a tiny trickle that somehow survived despite the odds. Enormous numbers. Far more than should be possible if time were absolute. The explanation is time dilation. A muon traveling at 99.94% of the speed of light has a gamma factor of about 29. This means that from our perspective on the ground, the muon's internal clock runs 29 times slower. Its half-life from our perspective is not 2.2 microseconds, but 64 microseconds. In 64 microseconds, at nearly the speed of light, the muon can travel nearly 20 kilometers, easily enough to reach the ground. From the muon's perspective, it still only lives for 2.2 microseconds. But from its perspective, the distance to the ground is length contracted by the same factor of 29. The 15-kilometer distance appears to be only about 500 meters. So from the muon's perspective, it only needs to travel 500 meters, which it can easily do in 2.2 microseconds at near light speed. Both perspectives agree on the outcome. The muon reaches the ground. They just disagree on whether it was because time stretched or space contracted. Both are correct descriptions in their respective reference frames. This is happening right now. As you sit here, muons are passing through your body at a rate of roughly 1 per square centimeter per minute. Every one of them is a tiny proof of time dilation. Every one of them survives its journey through the atmosphere only because its time is dilated relative to ours. This is not theory. This is observable, measurable, and happening continuously. Second, particle accelerators. At CERN in Geneva, Switzerland, the Large Hadron Collider accelerates protons to 99.999991% of the speed of light. At this speed, the gamma factor is approximately 7,461. This means that from our perspective in the laboratory frame, a clock traveling with those protons would tick 7,000 times slower than ours. This has practical consequences. Particles that are normally unstable and decay in microseconds can, at these speeds, survive for milliseconds from our perspective. Their lifetimes as measured in the lab are extended by exactly the factor that relativity predicts. This is measured routinely. It is not a special experiment done to test relativity. It is just part of normal operations. The entire design of particle detectors accounts for time dilation. If time dilation were not real, particle physics experiments would give completely wrong results. The fact that they give precisely correct results, experiment after experiment, year after year, is overwhelming confirmation. Third, and I mentioned this earlier, but let me go deeper, the global positioning system. Each GPS satellite orbits at about 20,200 kilometers above Earth's surface, moving at roughly 14,000 kilometers per hour. Special relativity predicts that their motion causes their clocks to run slower than ground clocks by about 7 microseconds per day. But general relativity, which extends special relativity to include gravity, predicts that being higher in Earth's gravitational field, where gravity is weaker, causes their clocks to run faster by about 45 microseconds per day. The net effect is that GPA's satellite clocks gain about 38 microseconds per day relative to ground clocks. 38 microseconds sounds tiny, but the speed of light is about 300,000 kilometers per second. In 38 microseconds, light travels about 11.4 kilometers. Since GPS works by timing how long light-speed radio signals take to travel from satellites to your receiver, an error of 38 microseconds translates to an error of about 11 kilometers in position per day. This would compound and make GPS completely useless within hours. The fact that GPS works at all, to a precision of a few meters, is because relativistic corrections are programmed into every satellite. This is not optional. It is not a minor adjustment. It is fundamental to the system's operation. Fourth, direct clock comparison experiments. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, demonstrated time dilation at everyday scales. They used aluminum ion clocks, the most precise timepieces ever built, and showed that raising a clock by just 33 centimeters, about 1 foot, made it tick faster due to the slightly weaker gravity at that height. They also showed that making a clock move at speeds as low as 36 kilometers per hour, the speed of a fast jog, caused detectable time dilation. These are not theoretical predictions awaiting confirmation. These are measured facts, published in the journal Science in 2010. The precision of modern atomic clocks is so extraordinary that they can detect the time dilation caused by taking a few steps up a staircase. So let us be completely clear. Time dilation is not a theory in the colloquial sense of the word. It is not a guess. It is not a hypothesis. It is not something that might be true. It is measured, confirmed, replicated, and relied upon every single day in technology that billions of people use. It is as established as the fact that Earth orbits the Sun. More established, actually, since we have measured time dilation with far greater precision than we have measured any astronomical orbit. Now, let me take you through one of the most famous and most commonly misunderstood aspects of time dilation: the twin paradox. This thought experiment has been discussed, debated, and confused about for over a century. And when you understand it fully, it illuminates the deepest aspects of how time dilation actually works. Here is the setup. Two twins, let us call them Alia and Zara. They are exactly the same age. On their 30th birthday, Zara boards a spaceship capable of traveling at 90% of the speed of light. She travels to a star system 10 light-years away. She reaches that star, immediately turns around, and comes back to Earth at the same speed, 90% of the speed of light. Let us calculate what happens. From Earth's perspective, the star is 10 light-years away. At 90% light speed, it takes Zara about 11.1 years to get there, and 11.1 years to get back. Total trip from Earth's perspective is about 22.2 years. When Zara returns, Alia is 52 years old, having aged 22.2 years. But what about Zara? She was traveling at 90% the speed of light. Her gamma factor is 2.294. So, from her own perspective, her clocks ran at 1 over gamma times the rate of Earth clocks. She experienced the journey taking 22.2 years divided by 2.294, which equals about 9.7 years. When Zara steps off the ship, she is about 39.7 years old. Her twin sister Alia is 52.2 years old. Zara is 12.5 years younger than her identical twin. Same birthday, same starting age, but now 12.5 years apart in biological age. Alia has grey hair and reading glasses. Zara still looks like she is in her late 30s. Same genes, same starting conditions, different ages, because time passed at different rates for them. Now here comes the paradox. The apparent paradox, that is. It goes like this. In special relativity, all inertial motion is relative. From Zara's perspective on the ship, she could claim that she was stationary and Earth moved away from her at 90% light speed, traveled 10 light years away, and came back. If all motion is relative, then should not Alia have aged less? After all, from Zara's perspective, it was Alia who was doing the moving. Should not the situation be perfectly symmetric? Should not they both claim the other has aged less? And if so, what happens when they meet? This seems like a logical contradiction. Both cannot be younger than the other. This is the paradox. The resolution is beautiful and illuminating. The situation is not symmetric. And the reason it is not symmetric is acceleration. Alia stays on Earth the entire time. She is in a single inertial reference frame for the entire duration of the experiment. She never accelerates. She never changes direction. She never switches from one inertial frame to another. Zara, on the other hand, does accelerate. She starts at rest on Earth, accelerates to 90% light speed, travels outward, decelerates when she reaches the star. Turns around, which requires enormous acceleration, accelerates back to 90% light speed in the return direction, and finally decelerates to stop when she reaches Earth. She has changed her state of motion multiple times. She has switched between different inertial reference frames. This breaks the symmetry. In special relativity, the principle that all inertial frames are equivalent only applies to inertial frames. That is, frames that are not accelerating. Zara's frame is not inertial for the entire trip because she accelerates multiple times. Alia's frame is inertial for the entire trip. And the mathematical rule is this. The person who remains in a single inertial frame for the entire experiment always experiences the most proper time. Anyone who deviates from this by accelerating, by changing direction, by switching frames, experiences less proper time. This is the deep geometric truth we discussed earlier. A straight world line through spacetime has the maximum proper time. Zara's world line is not straight. It bends at the turnaround point. Therefore, it has less proper time. Therefore, Zara ages less. Period. No paradox. Let me put it another way using the space-time diagram. If you draw Alia's world line on a space-time diagram, it is a straight vertical line going from their shared 30th birthday up to the reunion event. If you draw Zara's world line, it goes diagonally upward and to the right, then bends sharply and goes diagonally upward and to the left, meeting Alia's world line at the reunion event. Both world lines connect the same two events, departure and reunion. But Alia's is straight, Zara's is bent. In Minkowski spacetime geometry, the straight path has more proper time. The bent path has less. Alia experiences more time. Zara experiences less. And the difference is real, physical, and measurable. You might ask what happens during the turnaround. What happens during those moments of acceleration when Zara is changing direction? This is where things get particularly interesting. During the turnaround, from Zara's perspective, she experiences a force. She is pushed toward the front of the ship as it decelerates, then pushed toward the back as it accelerates in the return direction. During this acceleration, the equivalence principle of general relativity tells us that Zara can consider herself to be in a gravitational field. And in a gravitational field, time passes at different rates at different positions. From Zara's accelerating perspective, Earth is very far away in the direction of the gravitational field, and clocks higher up in a gravitational field run faster. During the turnaround, from Zara's perspective, Earth's clocks run very fast. Years of Earth time can pass during what is for Zara only a brief period of acceleration. This is where the missing time accumulates. This is how Zara can correctly account for the fact that Earth aged more than she did, even from her own perspective. The twin paradox is not really a paradox at all. It is a demonstration that time dilation is asymmetric when one observer accelerates and the other does not. And it has been confirmed experimentally. Every time we fly atomic clocks around the world, we are performing a version of the twin paradox. The traveling clock always returns younger. Always, without exception. The Hafele-Keating experiment I described earlier is literally an experimental twin paradox with atomic clocks playing the role of the twins. Now let me take you even further. Let me describe what would actually happen to you, physically, experientially, if you were to travel at velocities close to the speed of light. Because the mathematics tells us something extraordinary about how the universe would appear. First, let me talk about length contraction. This is time dilation's partner effect. Just as your time is dilated from the perspective of a stationary observer, so the length of everything in your direction of travel is contracted from your perspective. If you are traveling toward a star 10 light-years away at 99.99% of the speed of light, that star does not appear to be 10 light-years away from your perspective. It appears to be only about 0.14 light-years away. The entire universe ahead of you is compressed, squeezed in the direction of your travel by the gamma factor. This means that from your perspective, you can reach incredibly distant places in a remarkably short amount of time, because those places are not as far away in your reference frame as they are in the reference frame of someone who is not moving. This is why it is actually possible, at least in principle, for a human being to travel to the other side of the galaxy in a single human lifetime. The Milky Way is about 100,000 light-years across. If you could somehow accelerate to 99.999999% of the speed of light, the gamma factor would be about 70,700. The galaxy, from your perspective, would be length contracted to about 1.4 light-years across. At nearly the speed of light, you could cross that in about 1.4 years. You would age only 1.4 years. But on Earth, 100,000 years would pass. When you arrived at the other side of the galaxy, human civilization as you knew it would be ancient history. Every building you had ever seen would be dust. Every person you had ever known would be a distant ancestor to whoever now lived on Earth. The language you speak would be as dead as ancient Sumerian is to us now. You would have made the journey in the prime of your life. But you would have sacrificed 100,000 years of shared time to do it. Second, let me tell you about what you would see. Not just the time and distance effects, but the actual visual experience of traveling at relativistic speeds. This is even more bizarre than you might expect. There is an effect called relativistic aberration. When you travel at high speed, the directions from which light arrives become distorted. Light that would normally come from the sides gets shifted toward the front. It is as if the universe ahead of you is gathering in toward a single point. Stars that are beside you appear to move forward. Stars that are behind you shift toward the sides. At very high speeds, the entire sky, all the stars from every direction, crowds into a small disk directly ahead of you. The rest of the sky goes dark. This is not because the stars behind you have disappeared. It is because their light has been aberrated, shifted forward by your motion. The universe literally appears to concentrate ahead of you and vanish behind you. Then there is the relativistic Doppler effect. Light coming from ahead of you is blue shifted. Its frequency increases. Its wavelength gets shorter. Stars ahead of you appear bluer, more energetic. At very high speeds, visible light from ahead becomes ultraviolet, then X-ray, then gamma ray. You would need special shielding to survive the radiation from ahead. Meanwhile, light from behind you is red shifted. Visible stars behind you would shift into infrared, then microwave, then radio waves. They would become invisible to your eyes. So not only does the sky compress into a forward disk, but that disk shifts out of the visible spectrum at extreme speeds. At very close to the speed of light, you would need specialized detectors to see anything at all. The universe of visible light would have been shifted entirely into either gamma rays ahead or radio waves behind. Part 2. These are not speculative predictions. They follow directly from well-tested physics. Computer simulations have been created showing what the sky would look like at various fractions of light speed, and the results are otherworldly. At 50% light speed, the effect is noticeable but not overwhelming. Stars ahead appear slightly bluer and closer together. Stars behind appear slightly redder and more spread out. At 90% light speed, the distortion is dramatic. The forward hemisphere of stars has compressed into a cone of about 50 degrees, and those stars are noticeably blue shifted. At 99%, nearly all stars are crammed into a narrow forward cone, intensely blue shifted, while the rest of the sky is nearly empty. At 99.9%, the entire observable universe has collapsed into a tiny blazing disk straight ahead, consisting of radiation shifted far beyond the visible spectrum. And through all of this, inside your ship, you notice nothing unusual. Your heartbeat is normal. The lights in your cabin are normal color. Your food tastes normal. Time passes at its usual rate from your perspective. The strangeness is all outside. The universe has reconfigured itself around you. Now there is another effect I want to discuss. The increase in what we call relativistic kinetic energy and the related concept of relativistic momentum. In Newtonian physics, the energy of a moving object is 1/2 times mass times velocity squared. Simple, straightforward, and as you increase velocity, kinetic energy grows in proportion to the square of velocity. Double the speed, quadruple the energy. In this framework, there is no speed limit. You can keep accelerating forever. But in special relativity, this formula breaks down at high speeds. The correct formula for total energy of a moving object is gamma times m times c squared. At low speeds, this approximately reduces to the rest energy mc squared plus the Newtonian kinetic energy 1/2 mv squared. But at high speeds, it diverges wildly from the Newtonian prediction. The energy required to accelerate an object increases without bound as the object approaches the speed of light. To reach exactly the speed of light, you would need infinite energy. Literally, infinite. Not merely very large. Infinite. Since we do not have infinite energy and never will, no object with mass can ever reach the speed of light. It can get arbitrarily close. 99%. 99.9%. 99.9999999%. but never exactly 100%. Each additional 9 requires roughly 10 times more energy than the last. This is why, even at facilities like CERN, with enormous amounts of energy available, particles reach 99.999999%, but not 100%. The wall is absolute. It is not a technical limitation. It is a fundamental property of spacetime geometry. Let me now connect this to something that might seem unrelated, but is actually intimately connected. Let me talk about gravity. In 1907, 2 years after publishing Special Relativity, Einstein had what he later called the happiest thought of his life. He realized that a person falling freely in a gravitational field experiences no gravity. If you are in an elevator and the cable snaps, during the fall, you float. Objects released beside you float with you. You are weightless. For those brief seconds of free fall, there is no experiment you can do inside that elevator to distinguish your situation from being in deep space far from any mass, in zero gravity. Conversely, if you are in a rocket accelerating at 1 g in deep space, there is no experiment you can do inside the rocket to distinguish your situation from standing on Earth's surface in Earth's gravity. This is the equivalence principle. Gravity and acceleration are locally indistinguishable. They are the same thing experienced from different perspectives. And this principle, once you follow its logic, leads inexorably to a stunning conclusion. If acceleration causes time dilation, and gravity is equivalent to acceleration, then gravity must also cause time dilation. Clocks in stronger gravitational fields must tick slower than clocks in weaker gravitational fields. A clock at sea level must tick slower than a clock on a mountaintop. A clock near a black hole must nearly stop compared to a clock far from any mass. Einstein spent 8 years working out the mathematics of this idea, finally publishing his general theory of relativity in November 1915. And the predictions were confirmed. First by the Pound-Rebka experiment in 1959, where scientists at Harvard measured the gravitational redshift of gamma rays traveling up a 22.5-meter tower. The photons at the bottom of the tower were in slightly stronger gravity, and the frequency measured at the top was slightly lower, by exactly the amount general relativity predicted. Then by numerous other experiments over the following decades, growing ever more precise. Today, gravitational time dilation is measured routinely. As I mentioned, modern atomic clocks can detect the time dilation from a height difference of just 1 centimeter. The clock on your desk ticks at a slightly different rate than the clock on your floor. The difference is far too small for any human to perceive, but it is there, and it is real. Near extreme gravitational objects, the effect becomes enormous. On the surface of a neutron star, where gravity is about 2 billion times stronger than on Earth's surface, time runs roughly 20 to 30% slower than in deep space, depending on the star. Near the event horizon of a black hole, time dilation becomes infinite from the perspective of a distant observer. A clock hovering just above the event horizon would appear to an outside observer to be nearly frozen, ticking once per century, once per millennium, approaching absolute stillness as it gets closer to the horizon. From the perspective of the clock itself, time passes normally, but anyone watching from a safe distance would see it essentially stop. This means that black holes are, in a very real sense, time machines. If you could park a spaceship in a stable orbit very close to the event horizon of a black hole, but not so close that you fall in, time would pass much more slowly for you than for the rest of the universe. You could orbit for what feels like a few hours, leave, and find that years or decades or centuries have passed elsewhere, depending on how close you got to the horizon. This is not science fiction. This is a straightforward prediction of general relativity, which has passed every test ever thrown at it with flying colors. The movie Interstellar actually depicted this with reasonable accuracy. In that film, characters visit a planet orbiting very close to a massive black hole. On that planet, 1 hour equals 7 years on their ship and on Earth. This is not an unreasonable depiction. For a planet orbiting near the innermost stable circular orbit of a sufficiently massive, rapidly spinning black hole, time dilation factors of this magnitude are physically possible. The physics is sound, even if the exact numbers require specific conditions. Now, I want to connect time dilation from speed and time dilation from gravity into a single unified picture. Because they are not really two separate phenomena, they are two aspects of the same underlying reality. In general relativity, both velocity and gravity are described in terms of the curvature and geometry of spacetime. Gravity does not pull you through space. Gravity is the curvature of spacetime itself. Objects moving freely through curved spacetime follow the straightest possible paths, called geodesics, and these paths look to us like gravitational orbits and falling trajectories. Time dilation, whether from velocity or from gravity, is a consequence of the geometry of the path you take through spacetime. Longer paths through spacetime, in the Minkowski sense, correspond to more proper time. Shorter paths correspond to less proper time. Both high velocity and strong gravity create circumstances where your path through spacetime becomes shorter in the Minkowski sense, and therefore you experience less proper time. This is the grand unification. It is all geometry. The shape of your path through the four-dimensional fabric of spacetime determines how much time you experience, and both speed and gravity affect that shape. Let me now take you through some specific scenarios to really drive home what time dilation means for hypothetical space travelers, because the numbers are astonishing. Scenario 1. You board a spaceship and travel to Mars at 50% the speed of light. Mars, at its closest approach to Earth, is about 55 million kilometers away. At half the speed of light, about 150,000 kilometers per second, this trip takes about 6 minutes. At this speed, your gamma factor is 1.155, meaning time passes about 15% slower for you than for someone on Earth. Over a 6-minute trip, this amounts to a difference of about 54 seconds. You arrive at Mars having aged about 54 seconds less than your colleagues on Earth. Not dramatic, barely detectable without atomic clocks, but real. Scenario 2. You travel to our nearest stellar neighbor, Proxima Centauri, 4.24 light-years away, at 99% the speed of light. From Earth's perspective, the journey takes about 4.28 years. 4.24 light-years of distance divided by 0.99 light-years per year gives approximately 4.28 years. But your gamma factor at this speed is 7.09. From your perspective, the trip takes 4.28 divided by 7.09, which equals about 7.3 months. You experience about 7 months of travel. You arrive at Proxima Centauri having aged 7 months. But on Earth, 4 years and 3 months have passed. Your children are 4 years older. News from Earth is 4 years stale. This is no longer negligible. This is a meaningful divergence between your personal time and Earth's time. Scenario 3. You travel to the center of the Milky Way galaxy, about 26,000 light-years away, at 99.9999% the speed of light. Your gamma factor at this speed is about 707. From Earth's perspective, the journey takes about 26,000 years. But from your perspective, it takes 26,000 divided by 707, which equals about 37 years. In 37 years of your life, you cross 26,000 light-years of space. You arrive at the galactic center at age 67, if you left at 30. But on Earth, 26,000 years have passed. 26,000 years ago on Earth, humans were painting caves and hunting with stone tools. The entirety of human civilization, from ancient Mesopotamia to the present day, fits within about 6,000 years. You have been gone for more than 4 times that long. Whatever you find when you send a message back to Earth, it will not be the civilization you left. It might not be the same species. Scenario 4. You travel to the Andromeda Galaxy, 2.5 million light-years away, at an even higher speed. Let us say 99.9999999% of the speed of light. Gamma at this speed is approximately 70,700. The trip from your perspective takes 2.5 million divided by 70,700, which equals about 35 years. You make the journey in 35 years of personal time. But on Earth, 2.5 million years pass. Homo sapiens has only existed for about 300,000 years. 2.5 million years ago, our ancestors were Australopithecus, barely using tools. What exists on Earth 2.5 million years from now is beyond imagination. Whatever intelligence remains there, if any, would be as far beyond us as we are beyond those early hominids. Scenario 5. This is perhaps the most physically realistic and also the most haunting. Instead of traveling at constant velocity, you accelerate continuously at 1g, the acceleration due to gravity on Earth's surface. This has the wonderful property that you feel normal gravity inside your ship the entire time. No floating, no extreme g-forces. You simply stand on the floor of your ship and feel exactly as heavy as you do on Earth. This is the most comfortable possible way to travel, and the results are stunning. If you accelerate at 1g for 1 year of your time, then decelerate at 1g for 1 year, you will have traveled a total of about half a light year and reached a peak speed of about 77% the speed of light. About 2.1 years will have passed on Earth. If you accelerate at 1g continuously for 10 years of your personal time, not turning around, just accelerating outward, you will have traveled approximately 14,000 light years. Earth will have aged approximately 14,000 years. After 20 years of ship time under constant 1g acceleration, you have traveled hundreds of millions of light years. Earth is hundreds of millions of years older. You have outlived not just every person, but potentially every species that existed when you left. After 30 years of ship time, you have traversed billions of light years. Earth is billions of years older. It may no longer exist. The sun may have become a white dwarf. The solar system as you knew it may be unrecognizable. After about 45 years of ship time under continuous 1g acceleration, you have crossed the entire observable universe. From your perspective, you are a middle-aged person who has spent their adult life on a ship. From the universe's perspective, tens of billions of years have elapsed. Stars have burned out. Galaxies have dispersed. The universe has grown cold and dark. This is the most remarkable implication of time dilation. A single human being, in a single human lifetime, could in principle traverse the entire observable universe. The distance is not the barrier. The barrier is energy. The amount of fuel required for continuous 1g acceleration for decades is beyond any current or foreseeable technology. Even with perfect matter-antimatter annihilation engines, the mass ratio, the ratio of fuel to payload, becomes exponentially absurd for long journeys. But the physics allows it. The geometry of spacetime makes it possible. If you can accelerate, you can go anywhere in one lifetime. You just can never come back to your own time. This brings up what I call the loneliness problem of relativistic travel. Every high-speed journey is a one-way trip through time. You can never return to the era you left. If you leave Earth in 2026 and travel for 10 years of your time at extreme speed, you do not return to 2036. You return to some far future date, maybe 25,000, maybe 2 million, maybe 10 billion, depending on how fast you went and how long you were gone. The people of your time are gone. The culture of your time is gone. The languages, the music, the food, the cities, everything you knew is archaeological record. You are a living fossil, an artifact from a bygone age walking among whatever inheritors of the future exist. This is not a technical problem to be solved. This is a fundamental feature of the universe. Time dilation makes interstellar travel physically possible within a single lifetime, but it simultaneously makes it a permanent farewell to your own era. The faster you go, the more you see of space, but the more of time you leave behind. It is the universe's trade-off. Space and time are connected. You cannot have more of one without sacrificing the other. This is not a cruel joke. It is not a limitation imposed by ignorance or primitive technology. It is the geometry of spacetime itself. It is how reality is built. Let me now take you into a realm where time dilation intersects with some of the deepest mysteries in modern physics. Quantum mechanics. Quantum mechanics is the physics of the very small. Atoms, electrons, photons, quarks. It describes how particles behave at microscopic scales. And for most of its history, quantum mechanics and relativity have existed in an uneasy tension. Both theories are extraordinarily successful in their own domains. Quantum mechanics predicts the behavior of atoms and molecules with breathtaking precision. Relativity predicts the behavior of space, time, and gravity with equal precision. But combining them into a single unified theory has proven to be one of the greatest challenges in all of physics. A challenge that, as of today, remains unsolved. One of the deepest incompatibilities between quantum mechanics and relativity involves the nature of time itself. In quantum mechanics, time is treated as a parameter. It is not a quantum observable, it is a classical backdrop against which quantum events unfold. There is no time operator in quantum mechanics. You cannot measure time the way you measure position or momentum. Time in quantum mechanics is fed in from outside the theory. It is assumed to flow at a constant rate, uniformly for all particles, and the equations evolve quantum states forward through this externally imposed time. In relativity, time is completely different. Time is dynamic. Time is flexible. Time depends on your reference frame, your velocity, and the gravitational field you are in. Time is woven into the fabric of spacetime and responds to the distribution of matter and energy. Time is part of what the theory describes, not an external parameter fed in from outside. This incompatibility is called the problem of time in quantum gravity. And it is not merely a philosophical quibble, it has real mathematical consequences. When physicists try to write down a quantum theory of gravity, following the procedures that work so well for electromagnetism and the nuclear forces, they run into profound difficulties. The Wheeler-DeWitt equation, proposed in 1967 by Bryce DeWitt, based on earlier work by John Wheeler, is one attempt at a quantum equation for the universe's gravitational field. And it has a remarkable property. It contains no time variable. The equation describes a static state. There is no evolution, no change, no flow of time. The equation says that the quantum state of the universe simply is. It does not become. This has led some physicists to speculate that at the deepest level, time does not exist. That it is not a fundamental feature of reality, but an emergent phenomenon, something that arises from more basic timeless elements, much like temperature is not a fundamental property of individual atoms, but emerges from the collective behavior of many atoms. This is highly speculative and deeply controversial within physics. But it illustrates how profoundly relativity's view of time challenges our ordinary conceptions. Now, despite this deep tension, there are areas where quantum mechanics and time dilation have been brought together experimentally. Modern atomic clocks are quantum devices. They work by measuring the frequency of quantum transitions in atoms, transitions between energy levels that occur at incredibly precise, well-defined frequencies. These clocks are so precise that they can detect time dilation effects from tiny changes in altitude or velocity. In 2010, as I mentioned, researchers at NIST used aluminum-ion optical clocks to detect time dilation at a height difference of 33 centimeters and at speeds equivalent to a fast jog. These measurements rely on quantum phenomena to detect relativistic effects. The quantum precision of the clock reveals the relativistic nature of time. Even more remarkably, in recent years, physicists have explored what happens when you put quantum systems into superpositions of states that experience different amounts of time dilation. In 2020, researchers published work exploring what they called quantum time dilation, analyzing situations where a quantum clock is in a superposition of different velocities or different positions in a gravitational field. In such cases, the clock is simultaneously experiencing different amounts of time dilation. This creates a kind of quantum uncertainty in how much time has passed. The clock does not have a single, definite reading. It is in a superposition of different readings, each corresponding to a different branch of the superposition. This is genuinely mind-bending. Not only is time relative, depending on your speed and position, but quantum mechanics allows you to be in a superposition of different speeds and positions simultaneously, which means you can be in a superposition of different time dilations simultaneously. You can be simultaneously aging at different rates. The universe does not even commit to a single answer for how much time has passed for you until something forces a definite outcome. Let me also address the question that many people ask when they first learn about time dilation. Can it be used for faster-than-light communication? Can quantum entanglement, that spooky action at a distance that Einstein himself was troubled by, allow us to send messages faster than light and thereby get around the time dilation barrier? The answer is no. Definitively no. Quantum entanglement is real. When two particles are entangled, measuring one instantly affects the state of the other, regardless of the distance between them. This has been confirmed by numerous experiments. But, and this is crucial, this cannot be used to send information faster than light. This is called the no-signaling theorem, and it is a proven mathematical consequence of quantum mechanics. The reason is that the correlations created by entanglement are only visible when you compare the results from both ends. No measurement on one particle alone reveals any information about what was done to the other particle. You need to bring the results together, which requires ordinary communication at or below light speed. So quantum mechanics does not provide a loophole. The speed of light remains the ultimate speed limit for information transfer, and time dilation remains an inescapable consequence of approaching that limit. There is another quantum connection worth exploring. The question of what happens to time at the smallest possible scale. In physics, there is a natural unit of time called the Planck time. It is derived from three fundamental constants: the speed of light, the gravitational constant, and Planck's constant. The Planck time is approximately 5.39 times 10 to the negative 44th power of a second. This is so short that even describing it requires absurd comparisons. In the time it takes light to cross a single proton. Approximately 10 to the negative 24 seconds, roughly 10 to the 20th Planck times have passed. The Planck time is to a second as a second is to approximately 10 to the 43rd seconds, which is trillions of times the current age of the universe. Many physicists believe, though it remains unproven, that time may not be continuous below the Planck scale. That is, there may not be such a thing as half a Planck time. Time might come in discrete chunks, like frames in a movie. Below the Planck time, the very concept of before and after might not be meaningful. Spacetime itself might have a granular structure at this scale, like pixels in a digital image. From far away, the image looks smooth and continuous. But zoom in enough and you see the discrete pixels. Similarly, our experience of smooth, flowing time might be an approximation that breaks down at the most microscopic level. This is where approaches to quantum gravity like loop quantum gravity and string theory become relevant. Loop quantum gravity, developed primarily by Carlo Rovelli, Lee Smolin, and Abhay Ashtekar starting in the 1980s, proposes that space itself is quantized, that it comes in discrete chunks whose size is approximately the Planck length. In this theory, time is not fundamental. It emerges from the relationships between quantum states of the gravitational field. There is no background time in which things happen. Instead, change is defined by the relationships between physical systems. String theory, the other major approach to quantum gravity, also has interesting things to say about time at the deepest level. In string theory, the fundamental entities are not point particles, but tiny vibrating strings of energy. The different vibration patterns of these strings correspond to different particles, and the theory requires extra dimensions of space beyond the three we experience. In some versions of string theory, time itself might be emergent from a more fundamental timeless description. These are all highly speculative and unresolved questions at the frontier of physics, but they illustrate a profound point. Time dilation, the subject of our main discussion, is actually the tip of an iceberg. Beneath the surface lies the question of what time actually is at the most fundamental level. And the answer might be that time is not fundamental at all. It might be a useful but approximate concept that breaks down when you probe deeply enough. But at the scales we are discussing, from atomic clocks to galactic journeys, time dilation is robust, well understood, and experimentally confirmed beyond any doubt. Let me now bring us to one of the most interesting and least discussed aspects of time dilation: its implications for the Fermi paradox and the question of intelligent life in the universe. The Fermi paradox is the apparent contradiction between the high probability of extraterrestrial civilizations existing, given the enormous size and age of the universe, and the lack of evidence for or contact with such civilizations. If the universe is billions of years old and contains hundreds of billions of galaxies each, with hundreds of billions of stars, where is everyone? Why have we not detected signals? Why have we not been visited? Time dilation offers a fascinating and underappreciated angle on this question. Consider a civilization that achieves relativistic travel. They send ships to other star systems at 99% the speed of light. For the travelers, the journey to a star 10 light-years away takes about 17 months. Quick and manageable. But for their home civilization, the travelers are gone for over 10 years. When the travelers arrive and send a message back, it takes another 10 light-years for the message to reach home. By the time the homeworld hears that the colonists arrived safely, over 20 years have passed at home. Now, scale this up. A civilization tries to maintain an interstellar empire spanning hundreds of light-years. Ships travel between colonies at relativistic speeds. But every trip creates a time gap. The travelers age months while their origin ages years. Messages take years or decades to travel between systems. Synchronization becomes impossible. You cannot have a coordinated civilization if different parts of it are experiencing time at dramatically different rates. Moreover, if a sufficiently advanced civilization decides to explore the galaxy by sending ships in many directions at relativistic speeds, those explorers might traverse the entire galaxy in their lifetimes. But from the galaxy's perspective, hundreds of thousands of years pass. The home civilization that sent them might rise and fall in that time. New civilizations might emerge. The original civilization might go extinct before its explorers reach their destinations. And the explorers, arriving at the far side of the galaxy, find themselves separated from their own era by geological timescales. This suggests that relativistic travel, rather than enabling galactic civilizations, might prevent them. Time dilation creates temporal isolation. Every high-speed journey fragments the traveler from their origin in time. An interstellar civilization might find that its very expansion tears it apart temporally. The edges of the civilization might be tens of thousands of years out of sync with the center. Cultural drift alone over such timescales would likely create civilizations that are alien to each other despite sharing a common origin. This does not solve the Fermi paradox, but it adds an important dimension to it. Perhaps advanced civilizations exist. Perhaps they have even explored the galaxy. But the temporal fragmentation caused by relativistic travel means they cannot maintain a coherent presence detectable to us. They pass through our epoch like ships in the night, separated from us not by space but by time. Now let me address something that I think is important. There are many misconceptions about time dilation floating around in popular culture, on the internet, in casual conversation. Let me address the most common ones clearly and directly. Misconception 1. Time dilation is just an illusion or a measurement artifact. This is completely wrong. Time dilation is physically real. It is not a trick of perception. It is not that clocks merely appear to run slow. They actually run slow. The Hafele-Keating clocks were actually behind. They did not just seem behind, they were. The muons actually survive longer. They do not just appear to, they physically do not decay as quickly. Twins who travel actually end up at different ages. This is real, physical, measurable, and has consequences for flesh and blood and atoms and cells. Misconception 2. You would feel time passing more slowly. This is wrong. If you were on a ship traveling at 99% the speed of light, you would feel completely normal. Your heartbeat would feel normal. Your thoughts would flow at their usual pace. Music would play at the right tempo. Your breakfast would take the usual time to eat. There is no internal sensation of time passing slowly. The effect only becomes apparent when you compare your clock with someone else's clock. From your own perspective, your time is always flowing at the rate of 1 second per second. It is only from another reference frame that your seconds appear longer. Misconception 3. If you go fast enough, you can go back in time. This is incorrect within standard special and general relativity. Time dilation only slows down your personal time relative to others. It never reverses it. You always move forward in time. You just move forward at different rates depending on your speed and gravitational environment. Going backward in time, traveling to the past, is not possible through time dilation alone. Some solutions to general relativity's equations, like rotating black holes or certain types of wormholes, theoretically allow closed time-like curves, paths through spacetime that loop back to their own past. But these solutions are extremely exotic, require forms of matter that may not exist, specifically negative energy density, and most physicists believe they are ruled out by quantum effects, even if classical general relativity allows them. Misconception 4. Special relativity has been disproven or is outdated. This could not be more wrong. Special relativity is one of the most thoroughly tested theories in all of science. Every particle accelerator experiment, every atomic clock comparison, every GPS correction, every measurement of particle lifetimes, every observation of cosmic rays confirms it. In over a century since its publication, not a single experiment has contradicted it. Not one. Physicists have tried very hard to find deviations from its predictions, because finding such deviations would be a monumental discovery pointing toward new physics. But none have been found. The theory is as solid as anything in science. Misconception 5. Time dilation only matters at impossibly high speeds. While the most dramatic effects occur near light speed, time dilation is present at any speed. It is just that at low speeds the effect is extremely small. But it is always there. GPS satellites experience it at their orbital speed. The Hafeel-Keating experiment detected it at airline speeds. Modern atomic clocks can detect it at walking speed. It is not something that turns on above a certain threshold. It is always present, from the slowest crawl to nearly the speed of light. It is a continuous effect that simply grows more pronounced with increasing speed. Misconception 6. Einstein must be wrong because quantum mechanics contradicts relativity. This reflects a deep misunderstanding. Special relativity and quantum mechanics are not in conflict. In fact, they have been successfully combined into quantum field theory, which is the framework underlying the standard model of particle physics. This is the most precisely confirmed theory in all of science. The predictions of quantum electrodynamics, which is a relativistic quantum theory of electromagnetism, have been confirmed to better than 10 decimal places. What remains unresolved is the unification of general relativity, the theory of gravity, with quantum mechanics. Quantum gravity is the unsolved problem. But this does not mean either theory is wrong. It means they apply in different regimes and that we need a deeper theory to describe situations where both quantum effects and strong gravity are simultaneously important, like the interior of black holes or the very first instant of the Big Bang. Now I want to explore something that follows from time dilation and that connects to our deepest philosophical questions about the nature of reality. The relativity of simultaneity. Here is what this means. In Newton's universe, if two events happen at the same time, they happen at the same time for everyone. If a bomb explodes in Tokyo and a bell rings in London at exactly the same moment, all observers everywhere agree that they were simultaneous. This seems obvious. Of course, two things either happen at the same time or they do not. How could that be relative? But in Einstein's universe, it is relative. Whether two events are simultaneous depends on the observer's state of motion. Let me give you a concrete example that illustrates this clearly. Imagine a very long spaceship passing by Earth at high speed. At the exact moment the center of the ship is aligned with you on the ground, two lightning bolts strike simultaneously, one hitting the front of the ship and one hitting the back. They hit simultaneously from your perspective, the ground observer. You see both strikes at the same time after accounting for the time light takes to travel from each end. Now, what does the person in the center of the ship observe? They are in the middle of the ship, equidistant from both ends. If the strikes were simultaneous in their frame too, they should see light from both strikes arrive at the same time, since both are equidistant. But here is the thing. The ship is moving forward, toward the front lightning strike and away from the rear one. The light from the front strike has less distance to cover because the ship's center is moving toward it. The light from the rear strike has more distance to cover because the ship's center is moving away from it. So the person on the ship sees the front strike first and the rear strike later. They conclude that the front lightning bolt struck before the rear one. They were not simultaneous. And here is the crucial point. Neither observer is wrong. It is not that one of them has been fooled or made an error. The events genuinely are simultaneous in one reference frame and genuinely are not simultaneous in another. Simultaneity is relative. It depends on your state of motion. This has profound implications for the nature of time and reality. If there is no absolute notion of now, no universal present moment that all observers share, then what does it mean for events to be in the past, present, or future? A common conclusion drawn from this is what physicists and philosophers call the block universe or eternalism. In this view, all of spacetime, past, present, and future, exists equally. The past is not gone. The future is not yet to come. Everything simply is. Your present moment is not cosmically special. It is just where your particular world line happens to be right now. Other observers, moving at different velocities, have different present moments that cut across spacetime at different angles. Your future can be someone else's present. Your present can be someone else's past. Not in a signal-sending way, but in the geometric structure of spacetime. Imagine spacetime as a loaf of bread. Different observers slice the loaf at different angles. Each slice is there now. Your slice is tilted one way. A fast-moving observer's slice is tilted a different way. Both slices are equally valid. Neither is more real than the other. This means the loaf, all of it, must exist. The future slices are not empty waiting to be filled in. They are already there, being cut at different angles by different observers. This is not universally accepted among physicists and philosophers. There are alternative interpretations. The growing block theory says the past and present are real, but the future is not yet determined. Presentism says only the present moment is real. These views have their defenders and their challenges. But the block universe view is the most natural reading of what relativity tells us about the structure of spacetime. And it suggests that time as we experience it, as a flowing river moving from past to future, is in some sense an illusion. Not that time does not exist, but that its flowing nature may be a feature of our consciousness, rather than a feature of the universe itself. I want to be clear that this is a philosophical interpretation, not a proven fact. Relativity tells us the geometry of space-time. It tells us that simultaneity is relative, and that different observers divide space-time differently. But it does not definitively resolve the philosophical question of whether the future already exists. That remains an open question at the intersection of physics and philosophy. But what is definitively established, beyond any philosophical ambiguity, is the physical reality of time dilation. Whatever time ultimately is, at the deepest level, its observable behavior is exactly what Einstein described. It is relative. It depends on speed and gravity. It is not the same for everyone. And the faster you travel, the more of it the rest of the universe experiences without you. Let me now talk about something that bridges from our current technology to future possibilities. The question of whether we could ever actually build a ship that could demonstrate extreme time dilation. What are the engineering challenges? What are the physical limitations? What is theoretically possible, even if not currently practical? The fundamental challenge is energy. As we discussed, accelerating an object with mass closer to the speed of light requires exponentially increasing amounts of energy. Let us put some numbers on this. Consider a spacecraft with a mass of 1,000 kilograms, roughly the mass of a small car. To accelerate this to 10% the speed of light, you need kinetic energy equal to about 4.5 times 10 to the 17 joules. This is roughly equivalent to the total annual electricity consumption of a medium-sized country. To accelerate to 50% the speed of light, you need about 1.5 times 10 to the 19 joules. This is roughly the total annual energy consumption of all of human civilization. To accelerate to 90% the speed of light, you need about 7.7 times 10 to the 19 joules. To accelerate to 99%, about 5.4 times 10 to the 20 joules. These are staggering amounts of energy for a 1,000 kilogram payload. And it gets worse. This is just the energy to accelerate. You also need to decelerate at your destination. And if you want to come back, you need to accelerate and decelerate again. The total energy is roughly 4 times the one-way acceleration energy. Furthermore, you need to carry your fuel, and carrying fuel makes your ship heavier, which requires more fuel, which makes it heavier still. This is the rocket equation problem, and for relativistic travel, it becomes exponentially brutal. Even with the most efficient fuel conceivable, matter-antimatter annihilation, which converts 100% of mass into energy via E equals mc squared, the mass ratios become absurd. To reach 99% the speed of light and decelerate at the other end, you need a fuel-to-payload ratio of roughly 22 to 1. That means for every kilogram of payload, you need 22 kilograms of fuel. For a 1,000 kilogram payload, you need 22,000 kilograms of antimatter fuel, plus 22,000 kilograms of regular matter to react with it. 44,000 kilograms total, just for fuel, for a one-way trip with deceleration. And we currently produce antimatter in quantities of nanograms per year. At current production rates, it would take many trillions of years to produce enough antimatter for even a tiny relativistic spacecraft. There are alternative propulsion concepts that do not require carrying all your fuel. Solar sails and laser sails use external energy sources to push the spacecraft. The Breakthrough Starshot project, announced in 2016, proposed using a massive ground-based laser array to accelerate a tiny gram-scale spacecraft to 20% the speed of light. At this speed, it could reach Proxima Centauri in about 20 years. The time dilation at 20% light speed is minimal, about 2%, so this is not primarily a time dilation demonstration. But it would be the first human-made object to approach relativistic speeds. For dramatic time dilation effects, you need much higher speeds. And for higher speeds with laser sails, you need either more powerful lasers, larger sails, or lighter spacecraft. Alternatively, you could imagine harvesting fuel from the interstellar medium as you travel, the so-called Bussard ramjet concept. But analysis shows that the interstellar medium is too sparse to provide enough fuel at achievable collection efficiencies. The honest answer is that with current and near-future technology, we are nowhere close to achieving the speeds needed for dramatic time dilation in crewed spacecraft. We might achieve 20% light speed for tiny probes within a few decades if projects like Breakthrough Starshot succeed. But 99% or higher, the speeds where time dilation becomes truly dramatic, would require energy sources and engineering capabilities far beyond anything we currently possess or can clearly see a path to. But here is what is worth noting. The physics allows it. There is no law of physics that says it is impossible. The speed of light is a limit, yes, but the speed of light is not the threshold for dramatic time dilation. 99% is enough for a factor of 7. 99.9% gives you a factor of 22. These speeds, while extraordinarily difficult, are not physically impossible. They are engineering challenges, not physics impossibilities. A sufficiently advanced civilization, one that could harness the energy output of stars or master antimatter production at scale, could in principle achieve relativistic travel and thereby exploit time dilation for journeys across the galaxy. Now let me talk about one of the most beautiful and perhaps most melancholy implications of everything we have discussed. The one-way time travel problem. Time dilation is functionally a time machine. It allows you to travel into the future, not metaphorically. Literally, you get on a ship, travel fast for a while from your perspective, and arrive in the future. Any future you want. Want to see Earth 1,000 years from now? Travel at 99.999% light speed for about 17 months. When you return, 1,000 years will have passed. Want to see 1,000,000 years from now? Travel at the same speed for about 140 years. Too long? Go faster. At 99.9999999% light speed. 1,000,000 years passes on Earth, while only about 2 weeks pass for you. This is real time travel into the future. But it comes with a terrible catch. You can never go back. There is no reverse gear. Once you have traveled into the future, the past, your past, is gone forever. You cannot return to it. You cannot see the people you left behind. You cannot fix mistakes. You cannot even send them a message saying you are fine. Because for them, depending on how far you went, you have been gone for centuries or millennia. They are all dead. Their descendants are dead. Their civilizations are possibly dust. This creates a scenario that science fiction has explored extensively, but that is worth contemplating seriously. Imagine a person diagnosed with a terminal illness that will kill them within a year. Current medicine cannot help. But medicine advances. Maybe in 50 years, a cure will exist. So this person boards a ship, travels at high speed for a few days or weeks of personal time, and returns to find that 50 years have passed. They seek medical treatment with 50 years of advancement available. If the cure exists now, they are saved. But everyone they knew is 50 years older. Their children are elderly. Their friends are gone. Their career, their home, their social world, all transformed beyond recognition. They traded their world for their life.